Hello friends, I welcome you in lecture number 54 on Laplace transform. In this lecture we will talk about Dirac's delta function, and this function is also known as unit impulse function. We will define what is Dirac delta function in this lecture, and we will talk about Laplace transform of Dirac delta function. So remember this also. Dirac delta function is sometimes known as unit impulse function also. So first we discuss how we can define Dirac delta function. So for that I consider one graph of a function, and using that graph we will try to define Dirac delta function. Suppose this is x-axis and this is y-axis, and suppose I consider some fixed interval. Suppose this point is a, and suppose this distance is say small k, then this point will be a plus k, and suppose value of function in this interval is f of t minus a. We are going to define one function which we will use this notation for that function, because this definition of this function depends on two numbers, number a as well as number k. So this is the reason why I am using this notation, f of t minus a suffix k. So suppose value of this function is non-zero in this interval only, in the interval a to a plus k. Suppose value of function is non-zero, and outside this interval value of function is 0. So f of t minus a suffix k equal to 0 otherwise, and in between a to a plus k, suppose value of function is 1 divided by k, and if this much distance is 1 by k, then we will have this type of graph of a function between these 2 points at point a up to a plus k. So in this interval function has constant value, it is 1 by k, and this function is denoted by f suffix k t minus a. Now suppose we are reducing this length of this interval. Suppose we consider reduction of this length. Suppose we reduce this number k, or suppose we consider this small interval as compared to this. Suppose I consider this much interval, then I will have this type of graph. I am reducing the size of the interval, and definition of this function is same. It is 1 by k in between these two values and 0 otherwise. So if I consider or if I reduce the size of this interval, then I will have this type of graph of the function. Suppose I keep on reducing. Suppose I consider the interval which is small as compared to this interval. Suppose I consider this much interval only, a to a plus k, and I keep the definition same. So what I am doing here, I am reducing the size of the interval, that is I am defining this function in the interval a to a plus k, and I consider this number k, I am taking k as decreasing. So I am considering k very small, that means I can say that I am taking k tending to 0. So if I reduce the size of the interval as I have shown here, first I consider this much size, then I reduce up to this size, then again I reduce this size. So what I am doing, I am taking limit of this function as k tending to 0. So if k is reducing, or if this size is reducing, then we will have this type of situation, that this is going to be larger and larger Okay, if you consider another small interval, suppose this much interval, then this is going to be larger and larger, and this is reducing. So if I take k tending to 0, and if I consider limit of this function as k tending to 0, then this interval size will be reduced more and more, and we will have this type of situation that our function will be non-zero at point A only. If I take k tending to 0, then this interval is going to be interval with same endpoints, that means point A itself. So at if I consider limit k tending to 0, then at point A value of function will tend to infinity, because we are taking k tending to 0 and our function in this interval is 1 by k. So if I consider limit as k tending to 0, I will have 1 by k, that becomes infinity. So I have this type of function infinity if t equal to a, not for okay, this is at t equal to a, that is in this interval, that means at point a, and outside this, that is except t equal to a, function is 0. So this function, which is defined as a limit of f suffix k t minus a, is called Dirac delta function, and it is denoted by delta t minus a. So remember, delta t minus a is defined as the limit of the function which we have denoted by f suffix k t minus a, and that function is defined as 1 by k in the interval a to a plus k and 0 otherwise. And if we consider limit of this function fk at t minus a, then this limit will be another function, and that function is known as Dirac delta function or unit impulse function. So this Dirac delta function is taking non-zero value at only one point t equal to a, and it is 0 otherwise, and we will have this type of short impulse at point a. So that is the reason why it is known as impulse function. Sometimes we will have very short impulse and it is 0 outside this interval. So this is the way how Dirac delta function is defined, and I have written this systematically. Suppose they ask you to write down the definition of Dirac delta function or unit impulse function, you can write in this way. First we define the function fk t minus a, which is having value 1 by k in the interval a to a plus k, and value of this function is 0 outside this interval. And Dirac delta function is defined as limit of this function as k tending to 0. So write down in this way if they ask the definition of Dirac delta function. Dirac delta function is also known as unit impulse function. And remember, this Dirac delta function is not a function in the ordinary sense as we consider in calculus, but it is a function so called as generalized function. This type of function is known as generalized function. It is not behaving like a function which we consider in calculus, and we can write in this way also: delta t minus a equal to infinity at only one point a and 0 otherwise. And if we consider the integral of delta function from 0 to infinity, then it is always 1. That we can understand using this definition. Suppose we are interested in the integral of this function f suffix k t minus a. So we know that this function is non-zero in that interval only a to a plus k. So outside this interval value of function is 0, and in this interval value of function is 1 by k. Integral is with respect to t. So if we integrate with respect to t, we have integral of dt as t and limits of t are from a to a plus k. 1 by k is constant, integral of 1 with respect to t, that is t, and then we substitute limits of t as a plus k and a, and we can see that we have 1 by k into k equal to 1, and because k is positive. So therefore now if you are interested in this integral of delta t minus a with respect to t, then using the definition of this delta t minus a, this we can write as limit of f of t minus a suffix k, and limit as k tending to 0, integral is with respect to t, and because integral is with respect to t, we can take limit outside the integral, and this is integral from 0 to infinity, integral of this function f of t minus a dt, and integral of this function we have just obtained as 1. So if we consider here 1, then we will obtain that limit of 1. This integral has value 1, therefore we can prove that integral of Dirac delta function along this interval 0 to infinity is always 1. So this is generalized function. We have seen that delta t minus a is having infinity value if t equal to a and it is 0 otherwise, and we know that the integral of a function which is 0 everywhere except at only one point is always 0, but this delta t minus a is not an ordinary function, it is a generalized function, therefore we are having its integral equal to 1. Integral is not 0 even if function is 0 everywhere except only one point t equal to a. So this is special type of function which is known as generalized function. So this is the function which is non-zero at only one point, and the area under the graph of this function is always 1. Now we are interested in the Laplace transform of Dirac delta function. So we can prove that Laplace transform of Dirac delta function is given by e raised to minus as. For that, first we find out Laplace transform of this function, and then we will take its limit as k tending to 0. So again we recall this we define as it is non-zero in the interval a to a plus k and 0 outside this interval. Value of this function is 1 by k and 0, and if we want to obtain Laplace transform of this function, first we express this function in terms of unit step function. So we consider this interval whose endpoints are a and a plus k. So this we can write as difference of unit step function at these 2 points, u of t minus a and u of t minus a plus k, and then this we can again rewrite as 1 by k times u of t minus a minus 1 by k times u of t minus a plus k, and this is 0 outside this interval. So we have first expressed this function f of t minus a in terms of unit step function, and now we take Laplace transform on both sides. Laplace transform of f of t minus a equal to 1 by k is constant. Laplace transform of unit step function is given by e raised to minus as divided by s. Similarly here also, instead of a we have a plus k, so here we write e raised to minus a plus k s divided by k, and divided by s, not k. Laplace transform of unit step function u of t minus a is e raised to minus as divided by s. Here in this case, instead of a we have a plus k, and we can see we can take this quantity common. First we write this as e raised to minus as divided by ks. Here also we have k into s in the denominator. This I can rewrite as e raised to minus as into e raised to minus ks, and now I take e raised to minus as common, and this is also common, 1 by k into s, and here I have 1 minus e raised to minus k into s. So this is the Laplace transform of this function f of t minus a suffix k. Now Dirac delta function is limit of this function as k tending to 0. So we apply limit as k tending to 0 on both sides. So limit of Laplace transform of f k t minus a equal to limit k tending to 0, and this I can rewrite as e raised to minus as 1 minus e raised to minus ks divided by k into s. So I have to decide what is this limit, and on this side I can take limit inside the Laplace transform. So limit of Laplace transform equal to Laplace transform of the limit of f of k f suffix k t minus a, and here this e raised to minus as divided by s is independent of k, and therefore we can take it outside limit, and here we have 1 minus e raised to minus ks divided by k. Now left hand side is, this is limit of this function, which is nothing but delta t minus a. So here left hand side becomes Laplace transform of delta t minus a, and here we keep this as it is, and if you take k equal to 0, here you will have e raised to 0, that is 1, and 1 minus 1 is 0, and in the division also we have k. So this is 0 by 0 form, so that we can apply L'Hospital rule. So we differentiate numerator and denominator with respect to k. Derivative of k is 1. Here derivative is 0 minus e raised to minus ks into derivative of minus ks with respect to k, which is minus s. So let me rewrite this. This is e raised to minus as divided by s, and this I can rewrite as limit k tending to 0, negative negative positive, s times e raised to minus k into s. And now we take limit as k tending to 0, that means we put k equal to 0. So this is going to be s times e raised to 0. E raised to 0 is 1. So finally we have e raised to minus a into s as the Laplace transform of delta t minus a. So remember, Laplace transform of delta t minus a is equal to e raised to minus a into s. Suppose I consider a equal to 0, then Laplace transform of delta t will be equal to e raised to 0, that is going to be 1. So in this way we can find out Laplace transform of Dirac delta function using the definition of Dirac delta function, as well as we are using unit step functions. And from this you can have the formulas for inverse Laplace transforms of this right hand sides also. Suppose I am interested in the inverse Laplace transform of e raised to minus as, then from this formula I will write this as delta function at point A. Similarly, this formula will give me inverse Laplace transform of the constant function 1, which is equal to Dirac delta function at a equal to 0. So remember, this is very useful function whenever you will study your engineering subjects, especially this signal processing and digital signal processing, as well as sometimes power electronics. You will require this Dirac delta function or unit impulse function. So you will study this type of functions in your higher semester courses. There you will require this definition. So this is all about this session. In this session we have discussed what is Dirac delta function, and we have obtained the Laplace transform of Dirac delta function, and it is given by e raised to minus a into s. So this is all about this session. I hope you like it. Thanks for watching.